Can somebody tell me where the x-intercepts are, if there are any? Are there any x-intercepts? And if there are, where are they? Yes. Plus or minus 1 and 0. Okay. So we've got here, we've got the point 0, 1. Is that what you're referring to? Okay. So yeah, I agree. So is this on the x-axis or the y-axis? So yeah, I agree. Your y-intercept is going to be at 0, 1. And note, I'm denoting the y-intercept as a point. A lot of, sometimes it was asking, a lot of people were having problems with the homework in terms of not putting things in as points, and that's why I wasn't accepting. But where are the x-intercepts? So I absolutely agree. So somebody else, where are the x-intercepts? Yes. Absolutely correct. -2, 0, and 2, 0. These are the places where our function actually hits the x-axis. And that's my definition of what an x-intercept is. All right, let's talk about the domain and range. If I'm talking about domain, I'm talking about the set of what's inputs or outputs? Inputs. And we denote inputs with the horizontal axis, right? That's what we're putting into our function. So that said, where is the domain? Where's the lowest x value I can have in this particular situation? It's the lowest x value. -3, right? This is the lowest x value I can be at. Let me use red. I hope you see that a little bit better. -3, right? That's the lowest x value I can have here. What's the highest x value I can have? 3. All right. So the way I can write the domain, I can write the domain in 2 ways. So for domain, I could write it in 2 ways. The first way I could write it is using interval notation. In interval notation, note that -3 is actually a part, so it's included in my domain. So I use a bracket to denote that -3 is the lowest place that I can go. Does that make sense? And the highest value in my domain is +3, and it too is actually included. Now, if I had a hole there, so in other words, if instead of having this filled in dot, or I had something like this, where I had something with a circle with a hole in it, in that case, I would use parentheses to denote that this value is excluded. Y'all see the difference between included and excluded? If it's a dot, if it's actually a part of it, it's included. If it's an open hole, like you usually see something like this, then you use a parentheses for exclude. Does everybody see that? That makes sense. Now check this out. If I'm dealing with infinity, I always use, always, with infinity, use parentheses. Why? Because is infinity a number? No. Infinity is a concept. It's not a number. Everybody get that? So don't be like including infinity. It will get it wrong every single time because it's not a number. All right. Okay. So let's talk about the range. All right, somebody tell me, where's the lowest? Well, let me ask you this. For range, are we looking at, why did I put 2 N's on there? For range, am I looking at Y values or X values? Y, what's the lowest Y value I can have? Is it included? Yes, we can actually, we do have intercepts. So it's included. You want to use brackets there. Now, what's the highest Y value I could be at? 3, right? It's right here. 3 right here. So 3 included. Now, there's a second way I could denote this. The second way I can denote this is like this. I can say my domain exists when X is between 3 and -3, or -3 and 3. And note I use less than or equal to and less than or equal to. What I'm denoting is that my X value is bigger than -3, but it's smaller than +3. I'm about to say, someone trying to find their phone? All right, -3, but it's smaller than +3. Now, if I wrote it like this, would that be correct? Yes or no, and why or why not? So would this be correct? No, why? It does not include -3. Remember, if you want to include the value itself, we need to put that extra bar because we want to say that it's less than or equal to. All right. It's the same thing as putting a bracket as opposed to a parentheses. What about the range? Let me ask you this. Would this be a correct interpretation of the range? Yes or no? No, because? Okay, well, what if I said, I want the range to be looking like that? Is that a correct interpretation of the range? No, because why? Why? With range, we're talking about the Y variable. Yes, does that make sense? And the reason, of course, being that we're talking about where Y can be between 0 and 3. Everybody cool with that? Awesome. All right, let's move on. We're on page 21. So for those of you who have the book and you want to follow along, we're on page 21. I'm probably going to get through the first 4 problems. So I'm going to go to page 23. And then we'll have a 5-minute break and then we'll finish the rest of it. Sound like a plan? All right. Let's get to it. All right, when we're talking about increase or decrease, don't forget, don't worry, I have not forgotten the other parts of the bell ringer. We just hadn't covered it yet. So that's what we're doing now. All right, a function f is increasing on an open interval or on an interval I if for any choice of x1 and x2, in I, x1 is less than x2, we have f of x1 is less than f of x2. Now, for anybody reading that, it's like, what in the world does that mean? I like to think of it like this. Basically, think about this guy, and we'll call this guy, I don't know, we'll call him Bob. Okay, we got Bob. And Bob is going on a ski trip. Okay, if from left to right, he has to go up the hill, we will say that the function is what, do you think? Increasing. So basically, if you want to write this down, you can say, you can literally say something like increasing means going up the hill. Does not want me to dot the I in hill, but you get the idea. Increasing is like going up the hill. Now, conversely, suppose that Bob started skiing down the hill. That would be an instance of not increasing, but decreasing. You can think about decreasing as going down the hill. Now, note this occurs when you're going from left to right. Do y'all see that? It's always going from left to right. All right, let's take a look at number 1. Based on the graph on the right, find where the function f of x is increasing. All right, so we're looking at this function here. F of x is increasing from the point f -2, -4, -2 until it hits the point 0, 4. So those are the 2 points. Those are the 2 places where it's increasing. Let me ask you this. Is it increasing anywhere else? No, because between, say, 3 and 6, my function is doing what? Increasing, decreasing, being constant, what is it doing? It's decreasing, right? From -6, well, it's hard to look at, but it's -6 to -4. My function is also doing what? Decreasing, it's going down. So that's the only place it's increasing. So here's what we can say. We can say that f of x is, this is problem 1, is in, oh Lord, I'm struggling today. On the interval -4 to 0. Now, let me give you a quick kind of explanation of this. Number one, when we're talking on increasing on a particular interval, I'm talking specifically about which values, x values or y values? X. So if you say it's on increasing on the interval -2 to 4, you would be incorrect. Does that make sense? When we're talking about intervals, we're talking about x values only. Other thing about intervals, let me say this about MyLab. MyLab only recognizes brackets. I don't know why, because technically, we should be using parentheses. Now, why is that the case? Because at -4, we're not actually increasing or decreasing at that point, right? Because we're changing from decreasing to increasing. Y'all see what I'm saying? You can't be increasing and decreasing at the same point. So technically, we should exclude that value. However, MyLab Math does not see that. I don't know why, but MyLab Math wants you to put it in as brackets. And I have actually petitioned the company about that. But I'm just saying, for now, use brackets. Okay, I'm getting off my soapbox, but use brackets when you're doing your homework. Make sure you use brackets when you're doing your tests and quizzes and stuff. Everybody cool with that? Just use brackets there. Another way we can utilize that or say that is we're going to have -4 less than or equal to x less than or equal to 0. Once again, like I said, I don't like the fact that they do it that way, but it is what it is. I want y'all to get a good grade, so let's do what they say. All right, let's look at number 2. We're on page 21 still. Okay. All right, a function is decreasing on open interval. We kind of figured that out. So let's take a look at the question 2. Based on the graph on the right, find where the function is decreasing. So we're looking at this graph here. So I want you to take a look at this graph. I'm going to note some important points. So this is -6, this is -4. This over here is 3, this over here is 6. I know it's kind of hard to see. But I want you to, on your paper right now, say number 2, tell me which interval, use interval notation, and write down which intervals are decreasing. This is 0. Which intervals are decreasing? The answer's kind of up there, but I want you to practice using notation. Okay. Using interval notation, not a compound inequality. Using interval notation, what should I write for that first decreasing interval? Yeah. Yes. Everybody got that? So we use brackets just because that's what my lab wants us to use. And it's between -6 and -4. Anybody else want to tell me what I should write for the second decreasing interval? Because there's two of them. What should I write there? Anybody? Yes. Yes, a 6, yeah. Absolutely. Everybody got that? Now, we might also use this symbol in interval notation. That's a U, this right here. This U, this big U, it means union. It's just another way of saying and. Okay, so technically what we're saying is -6, -4, union 3, 6. So what we're saying is -6, -4, and 3, 6. It's just a mathematic notation. I'm not sure. I think if you're working on the homework, here's what I think. I think they want a compound inequality. I think what they want is this, and then they're going to say use a comma. For anybody who's already done some of these, is that what they want pretty much? Yes. They accept the union or either one? So they might ask for interval notation or they might ask for the comma. Okay, all right. Thank you. Everybody got that? Cool, cool, cool. All right, let's keep it moving. So, not too bad so far. All right, number 3. A graph is constant. It means it's not going up or it's going down. So once again, let's remember Bob. We got Bob. And basically, if he's not going up the hill or he's not going down the hill, he's just going straight in a straight line and right across, we can think about that as being constant. Did everybody see that? So I see something as a constant. That means even as X is moving forward and forward and forward, I am staying in the exact same position. So if you were to look at some points, you would see points like, I don't know, let's say this was 6 right here, okay? If this was 6, then what we could say is this would be like -3, 6 would be on here, -2, 6, 0, 6, 4, 6. You see what I'm saying? All of your X values would map to 6. Does everybody see that? Now, let me ask you this question. Is this a function? Yes or no? Yeah, a constant function is a function. It is a function. What's making this function weird? All of our outputs are 6. However, is it okay for your inputs to map to the same output? Yes, that is okay. Remember, the problem is when you have something like, if I added this value, this would be a problem. Why would I then have a problem in this case? If I added a -3, 2 to that, what would be the problem? Right, this input now has a different output down here. Everybody got that? That's the problem, of course, with functions and whatnot. All right, but these are functions. These are functions. Okay, so based on the graph to the right, find where the function f of x is constant. We can see quite clearly it's constant between these 2 points, 0, 3 with brackets, or 0 less than or equal to x less than or equal to 3 as a compound inequality. A function has a local maximum, okay, at C if there's an open interval at I containing C such that X does not equal C in I for f of C is less than f of c, we call f of c a local maximum of f. Okay, all of that mathematical mumbo jumbo basically just means this. If you get to the top of the hill, all right, so if you get to the top of the hill, we call that a maximum. Everybody see that? So we get to the top of the hill, we call that a maximum. If we go to get to the bottom of the valley, we're going to call that a what, probably? Minimum. We call these local maximums or local minimums because kind of these are situations, any situation where you go from increasing to decreasing, we're going to call that a minimum. And any situation where you go from decreasing to increasing, we're going to call that a, anywhere we go from increasing to decreasing, we call that a maximum. Any place we go from decreasing to increasing, we're going to call that a minimum. All right, let's take a look at problem number 4. Based on the graph, follow the answering the following questions. I'm going to write them down. So question A asks basically, what are the numbers where f, so what are the x values where f is as a local max? B asks, what are the local max? Basically your y value there. C asks, you all can go ahead and start answering these questions, by the way. Start working through that. All right, let's take a look at number A. Let's take a look at A. Let's find the x values where f has a local max. All right, so what point is the local max at? Is it -1, 1? Is it 3, 0? Is it 1, 2? Where is the local max going to be? 1, 2. This is one of those top of the hill situations here. All right. So that means the x value where there's a local max, we could say x is of course equal to 1 in this scenario. Everybody cool with that? Does that make sense? What is the local max? The local max is actually 2. Because when we say what the local max actually is, we're specifically talking, if I say something like, what is the value of the local maximum? It's talking about the y value there. What's the value of the local maximum? It is 2. What is the local maximum or maxima? That's going to be 2 in this particular instance. What are the x values where f is a local min? Well, we got 2 of them here, right? We've got this local min and this local min. We've got 2 of them. So we're going to say that x could either be 1 or -1, or it could be 3. Once again, we're on page 23 of the book. You're looking along with us on that. What are the local min? What are the actual values? What are the actual y values, guys? What's the one on the left? What are the 2 local min? 1, yeah. 1 and 0. 0 and 1, 1 and 0. Those would be correct. All right. So I'm going to give you a minute for E. Not a full minute, probably like 30 seconds. But I want you to write it not just in interval notation, but also in compound inequality notation. So the intervals of increase, there are 2 of them. We are increasing both between -1 and 1. And we're also increasing from 3 to infinity. All right, those are the two places where we're increasing. Now, how do we write those as compound inequalities? Well, the first one, we write this one as a compound inequality by saying x is between -1 and 1, like this. Not too bad. But how will we write 3 to infinity as a compound inequality? Or just an inequality, really. We can say what? How would you write that? If you're going to write x is between 3 and infinity, I don't think that's correct. How will we write that instead? Just, yep. You can say x greater than 3. It's either, technically it should be just greater than 3, but like I said, because it's probably going to take greater than or equal to 3, but that's what it is. Everybody see that? Because it's very specific. We're saying that x, your x value is bigger than 3. So obviously any number bigger than 3 fits all the way up to, you know, infinitely many positive numbers. All right, so that's increasing. Let's take a look at decreasing. My pen just stopped working. Oh, crap. Well, it is what it is. All right, so we've got intervals. We're talking about decreasing. The first interval we're going to be talking about is between negative infinity to -1. And we're going to denote that as x is less than or equal to -1. Note, less than or equal to has the, I guess I used, when I was teaching this, we used to draw little alligators. I don't know if y'all had that when y'all were being taught greater than or less than. But you have the little alligator teeth, they point towards the one that's bigger, right? So in this case, we can see that x should be the smaller one. That means we should be less than -1. All right, so x is less than -1. And also the other interval of decrease is between 1 and 3. All right, and we can denote that as x is between 1 and 3. Everybody cool with that? Okay, for each of graph the function y equals f of x, find the absolute max and find the absolute min if it exists. All right, so let's talk about this for a second. All right, so if I say something is an that's not an A. If I say something is an absolute max, that means it absolutely does not go further than that. Does that make sense? So for example, if I have the situation, which you all will see a whole lot in this course, which is y equals x squared, okay? I have what's called, in this function, this is an absolute minimum. Because yes, just like any other minimum, it goes from decreasing, the function is going from decreasing to increasing. It's the bottom of the valley, but it's absolute because there's absolutely no point that on this function that is less than that. Does that make sense? Well, it's called an absolute min. And this is the difference between a local min. I'll give you an example. So for example, if you have some function that looks kind of like that, okay? I've got a local max, local or relative max here. I have a local or relative max here, right? Those are maxes, but are they absolute maximums? Absolutely not, because obviously this part of the graph gets higher than those local max. Does that make sense? So I'm talking about absolute. I'm talking about absolutely no lower than that. However, if I cut this thing off, say here, like this, and I take a look, does this thing have an absolute minimum? Does it have an absolute minimum now? The answer is yes, and it's right here. Because are there any points that go lower than this point in this graph, the way it's drawn? No, so it's an absolute minimum. This right here would just be a local minimum. This would be your absolute minimum. Questions on that? Yes. In this situation, we would not have an absolute maximum because we still have this part of the graph. Yeah, that's a good question. In other words, we still have values that are higher than these. Yes. That's a good point. That's a good question. Whenever we're talking about the absolute maximum or absolute minimum, we're talking about a specific value. So infinity is not a value. It's a great question. Anybody else? Yes. Yes, that is a good point. Sometimes you don't have an absolute max or min. If I add this part back here, there are no absolute maxes, there are no absolute mins. Why? Because the function can go all the way to infinity, and the function goes all the way to negative infinity. Infinity, negative infinity, these aren't values. So we can't say there's a max at infinity. It doesn't work. So what we say is there is no absolute max or absolute min. Note, look at the last part of 5, or the question 5. What does the last part say? It says, if it exists, because it might not. Great question. Oh, I love this class. Y'all be asking good questions. All right, anybody else? All right, so let's do this exercise real quick. So if we look at A, we can see there is an absolute max here at 3.6, and there's an absolute min at 0.4 or 0.1 rather. Now, the reason why we know there's an absolute max and absolute min here, or hold on, let me ask you this question. So I'm telling you that the absolute minimum is at 0.1. Okay. Why is this a little bit different than the other minimums we've been looking at? Yes. So in this situation, it's not a bottom of the valley situation, is it? In other words, in this situation, it wouldn't be considered a local minimum because we're not going from decreasing to increasing. Does that make sense? It's an absolute minimum because this function does not go to infinity. This function does not go to negative infinity. It starts and ends here. So we can say it has an absolute minimum here. Everybody cool with that? Does that kind of make sense? All right. So let's take a look at B. What is the value? Listen to this question, because this question could be asked very in several different ways. So listen to how I'm phrasing this question. What is the value of the absolute minimum? What is the value for B of the absolute minimum? The value of the absolute minimum is what? Talking about value, I'm talking about what value? Am I talking about X? Am I talking about Y? What am I talking about? Y. So if I say, what is the value of the minimum? What is the value of the minimum for B? 1. Y'all see how I could ask this question in other ways? I could say something like, what is the X value? If I ask for the X value, I'm talking about X. But what is the X value where f of X has a local minimum? That would be X is equal to 3. Y'all see how I could ask this question differently. You got to be very careful on the homework as to what the question's actually asking you. Y'all see what I'm saying? Yes. It depends. It really depends on what the question's asking. So like if it's saying, what is the value of the minimum? It's talking about Y value only. If it's saying, where is the point or something like that, use the whole point. If it's saying, what's the X value, use the X value. And it is weird. It will ask you different questions based on, you see what I'm saying? Great question. So yeah, y'all get, I think y'all get it. So for the rest of these, I'm just gonna, what's I'm gonna do is this. You can see situations where, in this case, I messed this up. So I made a mistake. Anybody see why I made this mistake? So I said that the absolute minimum was at 1, right? And I was wrong. Anybody see why I was wrong? Because according to this, the absolute minimum does not exist. So what was I missing? And it might be kind of hard for y'all to see it, so I'm gonna blow this up. I want you to look very closely because I missed it. But look very closely at this minimum. What's the problem with this? Yes. Yeah. Back in the back. Right. The 0.31 isn't included. So what I did was I wasn't paying attention and I realized, oh, this is actually a hole there. So what we can say, please change your answer on your paper. But what we can say is the absolute minimum does not exist. Everybody got, yes. You would, that's a great question. So there's a, so let's kind of explore that for a second. If we like zoom in really, really close, we've got the next lowest point over would be actually not just 1 point, but it would be 2 points. You see what I'm saying? So like, for example, the next lowest point would be on both sides. Like if we got infinitesimally close to this point, it would be on both sides of that hole. And so since that's the case, we can't say there's an absolute min because technically there'd be two absolute mins because we're getting infinitesimally close to this hole. So the next minimum would be like right here. The other problem with that is this. After you get, so let's say I put a point right here, and let's say I put a point right here, right? Neither of those are a minimum anymore. I know it's weird, but neither one of these points that are infinitesimally close to what should be the minimum are doing that. And this has to do with something in calculus called limits. Great question. That's a great question, though. But yes, if there's a hole at the minimum, then we can say it's not a minimum. This is wouldn't even be considered a minimum. Okay, let's take a look at the others real quick, as I have completely destroyed this thing. So let me try to get back to where it was. Hopefully I can. That is correct. That is absolutely right. Yay, I kind of fixed it. Kind of. All right. Come on now. Work. We might just have to keep going. So it doesn't want to, it don't want to do right now. So let's move on to the next thing. All right, let's talk about even odd functions, determining even and odd from a graph, even and odd. When we're talking about an even or odd function, we're saying that something's even if, specifically, you can write this down, specifically f of negative x is equal to f of x. So I'll give you an example of that. If you have something like, let's go back to f of x equals x squared for a second. All right, f of x equals x squared. If I plug -2 into this function, I get out 4, right? Because -2 times -2 is 4, right? Plug -1 in, I get 1. If I plug in 0, I get 0. If I put 1, I get 1. If I plug in 2, I get 4. Are y'all following me so far, right? You're just squaring each of the numbers. I want you guys to know that if I plug in the negative version of the same value, I get the same number. This is why it's called an even function. So if I have -2 and I get 4, and I have +2 and I get 4, it's even. Another way to think about that is that graphically, it should be symmetrical over the y-axis, right? So it's a situation, you got that symmetry going. That's why it's called even. An odd function would be something like x, just actually y equals x itself. All right, so like for example, if I plug -2 in, I get -2 out, -1, -1, 0, 0, 1, 1, 2, 2. Well, I'm getting, for like the negative version, I'm getting the same absolute value answer out, right? For -2, I'm getting, absolute value 2. I'm getting absolute value 2. But what's changed here? What has changed between these 2 points? Yeah, so basically we've got -2 on one end and +2 on the other end. So the sign has changed. So for example, I'll give you another one. If you had x and say x cubed, all right, you'd have -2, -8, 1, -1, or -1, -1. You'd have 0, 0, you'd have 1, 1, you'd have 2, 8. Once again, still the same values, however, absolute values, but we're changing signs on either side. So that's what this means, and that's what this means. So if it's odd, that means it's changing values from negative to positive. However, if it's odd, that means that the absolute value remains the same. Do y'all see that? The absolute value remains the same. In other words, here's the theorem. A function is even if and only if its graph is symmetric with respect to the y-axis. Right? So we talked about that. These are these even functions. A function is odd if and only if it is symmetric about the origin. It has that origin symmetry we talked about in the first lecture. All right. Okay. Let's talk about some situations and figuring out whether they are even or odd. So determine whether each graph is an even function, an odd function, or a function that's neither. All right, so let's take a look at this. For A, this is an what? Even is absolutely correct. It's an even function because we can see it is symmetrical about the y-axis, right? So for example, let's say this was, 2, and let's say this was -2. They both yield the same value, say 1. So this would be 2, 1 over here and -2, 1 over here. It yields the same value, okay? And technically what that means is f of x is equal to f of -x. All right, what about B? Is it odd, even, or neither? It's weird, this one is neither. Now, why is that? Because it's not symmetrical about the origin. In other words, if I were, remember, symmetrical about the origin means if I were to take my graph and rotate it 180 degrees, I should see the exact same thing. If I rotated this thing about the origin 180 degrees, so if I rotate this thing about the origin 180 degrees, so I'll put this 180 degrees, I would have something that looks probably like that. Well, that wouldn't be it, right? This, or rather, not like that, but it just ain't it, okay? And then last but not least, this one, is it odd, even, or neither? This is odd. And you can see it does have that symmetry, that 180 degree origin symmetry. If I shift that around the origin, 180 degrees, I do get it. Hey, we got 10 minutes. Time flies. All right. So, well, time flies for me. I don't know about y'all. I've been here for an eternity. All right. Determine algebraically whether the given function is even, odd, or neither. So here's how you do it. The thing you want to do to determine whether it's even, odd, or neither is you're going to plug in f of negative x. Okay? You're going to plug in f of negative x. So let's do an example. So for a, I'm going to rewrite it so that we can see it a little bit better, but f of x equals 3x to the fourth minus 5x squared plus 10. And we're going to determine whether or not this thing is odd, even, or neither. So we're going to plug in negative x. So we plug in negative x, it's going to look like this. We're going to have 3 negative x to the fourth minus 5 negative x squared plus 10. Everybody seeing what I'm doing so far? Y'all rolling with me? Cool. All right. If I have negative x to the fourth, that means I'm going to multiply negative x by itself 4 times, right? You have negative x, then positive x squared, then negative x cubed, then positive x to the fourth. Y'all see that? It's going to switch from negative to positive, depending on how many times you go. So this will be positive 3x to the fourth. Everybody see that? Good, good, awesome. Negative x squared, that would be 2 times. So this would be negative x times just negative x. Now, if I have 2 negatives and I multiply them together, I get a positive. That's absolutely correct. And you know, with negative 5x squared, because that x squared is being positive plus 10. Now, lo and behold, this value is the exact same as this value. So since it's the exact same, we know this function is even. Very good. All right, let's do some more. Let's take a look at B. We got x cubed. We got x cubed, 4x cubed and minus 7x. So we got 4x cubed minus 7x. If I plug a negative in here, and before I even do anything, what do y'all think this is probably going to end up being? Just kind of looking at the values. It will probably end up being odd, right? We got some odd degrees here. It's a pretty good guess. So let's take a look. We've got negative x cubed. That means I got negative x times negative x times negative x 3 times. Now, if I do negative x times negative x, that means it's positive. But if I multiply negative x by another negative, that turns it back negative. So my final answer would be negative 4x cubed, because you're going to do it, it's going to be negative there. If I have negative 7 times negative x, that's going to give me positive 7x. Now, you'll note that these are the same values if I multiplied this bottom number by negative 1. Do y'all see that? And therefore, these are odd. So this would be an odd function. Because, yeah. All right, let's take a look at C. That's interesting. Let's take a look at C. By the way, we are on page 26. Page 26. All right. On page 26. I'm not going to even write the whole thing. Basically, I'm just say this. You got 5 times negative x to the fourth plus 9 times negative x cubed minus 4 times negative x squared plus 1. Negative x to the fourth, that's going to give you 5x to the fourth. Negative x cubed is going to be negative x 9x cubed. This is going to be negative 4x squared because the x squared is going to be positive, and plus 1. Now, is this odd, even, or neither? It is neither. Looks so promising in the beginning, but it's not. Why? Because it's one thing. First of all, it's not the same, right? So obviously it's not even. But secondly, if I plug -1 or I multiply -1 by everything, I don't get back to my original function. So since those two are not the case, this is a neither situation. D is neither as well. And actually what I'll do is I'll just remove the thing. We can kind of see it because we are running out of time. But we are going to finish. B is odd. C is neither. You said B was odd. D is odd. That's a good question. So let's take a look. No, so if we take a look closer here, get rid of that. There we go. All right, if we take a closer look at D, when you plug negative x in, right, you get negative x squared in the denominator, which gives you positive 7x squared. However, this negative in the numerator means that you have negative 5x, which gives you a negative in front of the whole thing. Note, this original is, and the negative of it, that means it's odd. So your result is the negative version of the original. If you multiply this by -1, you get back to this. So that's why it's odd. Great question. This one's neither, as you can see. The last one does end up being odd because if you take the 9th root of x, that makes it negative, and therefore negative x 9x. If this was an even number, if it was like the 8th root of x, it would then be actually would end up being it would end up being undefined, actually, because you can't have a negative of an even root. All right, let's talk about some basic functions. So we take a look at the square root function. This is like all square roots. Like, for example, the square root of 4 is 2, square root of 9 is 3, right? And these things look kind of weird. They look kind of like this. So kind of get used to the way those look. The next set of problems we'll talk about, we got the cube root. These are kind of like the square root, but they actually have a tail on this end. The reason those are different from the square root function is the square root function can only be positive as we can't have negative square roots, but you can have negative cube roots. The absolute value function, the way I think about it, absolute value with a V, it literally looks like a V. So all the absolute values on one side, 1, 1, 2, 2, 3, 3, and -1, 1, -2, 2, -3, 3 on the other end. We have some more out here. We got linear functions. These are lines, literally what they sound like, linear. Constant functions are constant all the way through. We talked about that. Square functions, we've been talking about a little bit. These are, anybody remember what this shape is called? Starts with a P. Parabola is a real weird word, but basically that's what these are. Cube functions are odd, and they kind of look like a guy who's got one arm down, one arm up. Reciprocal functions, we're going to get to that a little bit later in the course. Power functions, we're going to get to that a little bit later in the course as well. And we're going to talk about piecewise defined functions. All right, so give me 1 second, guys. It's really going to take maybe 30 seconds for me to explain this real quick. So if we're talking about a piecewise defined function, it has a lot to do with that, that lab we did, where remember we had the situation where the child was growing up and then his height as he continued to, be grown. Do y'all remember that? It kind of looked like this. A piecewise defined function basically tells you, hey, I'm going to zoom in a little bit so y'all can see it even more. But what it's saying is, hey, do this piece of information between these two x values, then do this piece of information at this value, and then do this piece of information at this value. In other words, if you look at the graph, you can see it's doing different things at different parts of the graph. Y'all see that? And that's why it's called piecewise. So what you do to solve these is you look first at the interval, and that tells you what to do. So for example, if you want to figure out f of 0 lies in this interval. So you would use 0, -0, +1. However, f of 2 lies in this interval. So we would use 2 squared. Do y'all see that? So determine what interval it's in first, then do what you need to do. And I'm sorry I'm a minute over, but that's it, guys.